Hey everybody, it's Brandon with FastDataScience.ai, and today what I want to do in this tutorial is talk a little bit about the relationship between descriptive statistics, inferential statistics, and more importantly, try and draw a connection between concepts that are related to those two areas of statistics and modern machine learning. So in this tutorial, we're going to cover some pretty big ideas. And let me just bring up my quick outline here. So we're going to talk a little bit about getting to statistical inference, understanding the role of sampling distributions, how the central limit theorem plays a role, understanding p-values in that context, and then really trying to understand all of these ideas in the context of more modern day machine learning, and as a lot of data scientists use these concepts in their day-to-day practices. So let's go ahead and jump in and get started. So one way that I often view the difference between descriptive statistics and inferential statistics is as a way of also talking a little bit about the difference between a data analyst and a data scientist. What do I mean by that? Well, typically in a day-to-day for a data analyst, they spend a lot of time using the tools of descriptive statistics to help describe data. And then they use that data to then report on and provide information to leadership or stakeholders, whoever it may be, on what those summary values, those statistics that are used to help summarize that data, are telling them about their analysis. As you start to sort of move into more advanced data analysts or data scientists roles, you start to use more inferential statistics in their day-to-day. And so talk a little bit about connecting these two roles and what some of the major concepts are that help us to understand how inferential statistics is applied to data science in the day-to-day kind of business environment. Okay, so descriptive statistics are really valuable because they help us do one really major function whenever we have lots of data at hand. So here's an example data set that's in a typical format where you have rows of observations and columns that represent variables or features or whatever you want to call them. And if we look at this just with the naked eye, we see really quickly that it's hard to really understand what all of these numbers mean. So descriptive statistics help us to derive some additional meaning from lots of numbers by reducing those into fewer numbers, some numbers that help us summarize all of this information. So most importantly, descriptive statistics are used, right, to describe those samples of data that we extract. And they allow us to then summarize that data to be able to tell stories about how that data might inform some decision making. Most important descriptive statistics are the mean and the standard deviation, particularly for numeric variables. I also find measures of min and max, or the range, quartiles, as well as missing values to be really important descriptive statistics that we can use to help us understand those samples of data that we're using. In addition, correlations are also another really valuable descriptive statistic. And correlations start to open the door to inferential statistics, and we'll talk a little bit about making that connection in a second. But most importantly, when it comes to describing data, we often see people, data analysts in particular, but also data scientists, in that sort of early phase of exploratory data analysis when they're just trying to understand the information value in a sample of data, leveraging these various descriptive statistics tools to start to understand what the data are representing. So here's an example of a descriptive statistical analysis of that data set that we just looked at. And in this particular case, we're using the describe method available in the pandas library. And what we're able to see is each numeric variable, its count, so how many times do we see values for that variable come up, so it gives us some sense of whether or not there are any missing values. It gives us the average, or the mean, for each of those variables. It also gives us the standard deviation, and then it gives us the minimum, the maximum, and the different values at each quartile. So if, for example, we were to jump over to question number 3 here, which is this column on the right, we would immediately see that the mean is 2.2595, the standard deviation is 1.07, and so we start to get some sense in the context of the minimum and the maximum, which is 1 and 5, that, okay, the mean is roughly right in the middle of that range. And so this is meaningful in telling us that question 3 might kind of approximate a normal distribution, which aids some of the things that we can assume about that variable as we start to make connections to inferential statistics. We'll come back to that in a little bit, but at the face value here, descriptive statistics are really valuable for helping us to understand the information value contained in each of these different variables and what it might tell us to help answer some business questions. Okay. So now what I want to do is talk a little bit about making the connection between those descriptive statistics that we calculate and then trying to use those to say something about data that we've never seen before, right? That data is represented in the population that we're trying to say something about. And that's where inferential statistics really comes in and makes for a lot of valuable uses, in that we can do something with our descriptive statistics and the sample of data that they were computed on to start to make some conclusions or statements about and get some confidence in how those things may help us understand the population that they were derived from, so that then we can make decisions that we feel are more reliable decisions because they may have a statistical likelihood of actually being representative of the population. So one of the core functions of inferential statistics is essentially to take descriptive statistics and use those descriptive statistics to estimate what those values may be in the population of that data. So in the case of the mean, on the left here, we have a sample distribution. So for example, one of the variables in that data set that we looked at a few slides earlier, say it's question number 3, maybe it's distributed in a way that looks like this whenever we just compute a frequency distribution, a histogram that allows us to see how the different values distribute within the data. And so we might find the sample mean here somewhere in the middle. Well, it turns out that the sample mean is actually a good and unbiased estimate. It's our best estimate of what we think the likely population mean is for that same variable. We'll come back to that in just a second, but another really popular statistic and valuable statistic is also the standard deviation. So we can also use the sample standard deviation to say something about the standard deviation we may see in the population. Now, unlike the mean, the sample standard deviation is a little bit biased in its estimate of the population standard deviation. So we do make a small correction. However, just simply assuming that the distribution of the population raw data centers around our sample mean and then some slightly corrected version of our standard deviation from our sample is not all that useful on its face value, right? So all we're really able to say is, well, we think our best estimates of the population are exactly what we found in the sample, with some variation around that average based off of a corrected standard deviation that we apply. But what do we do with that information? Well, where inferential statistics really becomes valuable is in being able to understand comparisons. So it's not the case that we're interested in what the raw average is necessarily for a particular population, but it is more often the case that we're interested in how does that average differ from another average or a whole bunch of other averages. Another way of looking at this problem is to also question, well, how does the relationship between two variables potentially relate, or more variables potentially relate to the relationship we might expect to see in the population? And this is where we're starting to really uncover how descriptive statistics can be applied to inferential statistics to help us come to meaningful conclusions about what that population might be telling us. And this is where we get into the sampling distribution and the central limit theorem. So knowing the distribution of sample statistics helps us to determine if our comparisons are quote-unquote statistically significant. In order to make these comparisons, we assume something really simple, and that is that those comparisons, whether it be two means that we're comparing, so maybe the mean of one particular group and the mean of another group on the same variable, say men versus women on that question number 3 to see if their differences are statistically significant, we assume that the differences should be 0. And with that assumption, what we can do is we can create a sampling distribution of mean differences. We can do the same thing with correlation values, where we assume that correlation values in a population should be zero. There should be no relationship. And what we want to test is, given the value we observe in our sample, how likely is it that that observation is actually different from the expected distribution, which expects that relationship to be zero. So what do I mean by that? So we often mean that essentially the population of mean differences, for example, should be zero, but we know that whenever we look at differences in means, they're not always going to be exactly zero. The population distribution of correlation coefficients should also be zero, even though we understand that if we were to select a lot of random samples and test correlations between two variables, they'll probably vary around the mean. What we learned from the sampling distribution is, regardless of how those variables are actually distributed in their raw form in the population, whether they're normal or they're skewed in their distribution, that what we can assume is that regardless of their population raw distribution, that the distribution of sampling statistics that was taken from them can be assumed to be roughly normal. Let me make a really quick demonstration of this. So what I'm going to show you here is how the sampling distribution of statistics roughly approximates a normal distribution in a lot of cases. So what we have here on the right is we have some code whereby I pull in some libraries that we're going to use to quickly analyze some data. I create a data frame, which you see I've already created here. That data frame has over 4,600 rows and it has 127 columns or variables. And so what I'm going to show you is we're going to take one of those variables. That variable is called reliable, and we're just going to take a look at how that variable is distributed in this data set. What you'll see is the distribution of the variable reliable in this particular data set. It actually has a slight skewed distribution, a negatively skewed distribution. So you see there are more values that are 4s and 5s than there are values that are 1s, 2s, and 3s. Now what I'm going to do is I'm going to run a loop 100 times, and I'm going to take a sample of that data, roughly 50% of the data, and I'm going to compute a mean after each sample. And I'm going to create a list of new means, so we'll have 100 new means. And what we're going to do is then we're going to plot those new means. So when we run this part of the code, it'll take just a few seconds here, but what we'll see is that now our distribution is starting to approximate a normal distribution. Again, note, this is the distribution of raw data, this is the distribution of sample means. And this phenomena turns out to be fairly robust across lots of different sample statistics types, including things like correlations and means. Okay. So with this information, what we're able to do is we're able to start making conclusions about the value of particular sample statistics, descriptive statistics, and whether or not those descriptive statistics that we're computing have any indication of being statistically significant in a population. So the central limit theorem does have some limitations. One of those limitations is that it can only be used when we can assume a finite variance in the population distribution. So in situations where we're leveraging linear models and we can safely assume that the variables in those linear models are roughly normally distributed, or at least not even normally distributed, right? Because we did say that they don't have to be in order for us to test the information value of the parameters that we're trying to estimate. But so long as we can assume that they at least have a finite variance, which isn't always true of more complex distributions or more complex models where the parameter distributions are unknown to us because those models are nonlinear. We'll come back to that. Cauchy distribution is one of those distributions that does not have a finite variance. It actually has an infinite variance. We also know that the central limit theorem is most useful when we can assume that there is homogeneity of variance, that means that essentially the variation in two samples of their distribution is roughly the same. So if we're comparing two means, those two means have roughly the same standard deviations. And we also need to assume that the observations are independent themselves as well. So why does all of this matter for machine learning? What's the application here? Remember that we can sort of characterize machine learning as a mapping of input data to some predictions. That is, some function that we apply to input data in order to get some prediction or some output. And so we can characterize most machine learning functions in this way, as y equals some function of x, where x is sample data that we're using to train the parameters of that function to be able to predict the values of y. A really simple example of this kind of model is a regression formula. This is the model or the equation for a line, right? A straight line in any given set of data. And in this case, all we're dealing with are two variables, x and y. I will point out that in this form, this model is purely descriptive. That is to say that A, which represents the point on the y-intercept where the line passes through it, and B in this case, which represents the slope of the relationship between x and y, are both simply descriptive statistics at this point. B, because all we're doing is comparing one variable to another, is also characterized by the correlation coefficient. What we want to be able to do in order to turn this regression formula that is describing our sample data into a model that we feel confident about and has application to a population outside of our sample data and will reliably be able to predict correct values in other data sets, is we need to be able to test whether or not these values that are a part of the model are statistically significant, and that the overall combination of them is also statistically significant in its predictions for y. So we can test different parts of this model using different types of inferential statistical tests. We can use tests of this correlation coefficient value, and remember, we assume that this value should be 0. So we can test whether or not this value relative to the size of the sample that it was trained on is statistically and significantly different from what we would expect, which would be 0. In addition, we can also test the performance of this whole model. Let me go back. On whether or not it accurately predicts the outcome using a different statistical test called an Ftest. We'll cover the Ftest in a future tutorial. For today, just know that what we're trying to do is to understand how descriptive statistics help us make a bridge to inferential statistics and what it means for machine learning. In other words, we can help answer this question: how do I know if my parameter estimates are good? That is, generalizable outside of just my sample data. Well, we can test the parameter against a known population distribution of sampling statistics to determine if the parameter estimate is statistically significant. In simple cases where we assume relationships are linear, we can generate expected distributions of repeated samples taken of sample statistics, hence our sampling distribution, to test if our observed statistic that we derived from our sample data is different from those expected distributions. So in inferential statistics, we use these concepts in order to help test different aspects of those linear models, as I pointed out, specific coefficients in a model, and the overall models, which uses a slightly different statistical test called an Ftest. In this particular concept, if we wanted to test whether or not our correlation coefficient was significantly different from 0, we would apply our correlation coefficient that we observed to our understanding of this roughly normal distribution. Again, the shape of this distribution is a sampling distribution, And that sampling distribution is determined, its actual shape is determined by the sample size that we used to derive our understanding of this shape. So it varies based off sample size. The larger the sample size, the more like a normal distribution this will represent. Nevertheless, what we do know is that we can use our information about the shape of this distribution to determine whether or not our observed coefficient is far enough away from the mean for us to conclude that indeed this is statistically significantly different. That is to say that this particular correlation coefficient represents a different distribution, one where the mean is not zero. In other words, there is a true relationship between the two variables that parameter is trying to estimate. And so here we see that estimate of this particular correlation coefficient as one example, how we apply it to identify if it's far enough away from what we would expect of zero. Not all machine learning models allow for these assumptions to test against. More sophisticated nonlinear models with unknown population distributions, particularly population distributions that may have finite variances, require different methods for us to be able to make any kinds of assumptions or conclusions about the suitability of a model in its application and performance to data beyond just the sample that model was trained on. Again, that's the fundamental goal behind inferential statistics. We can use our knowledge of simpler scenarios, linear distributions, sampling distributions, and the normal distribution based on the central limit theorem to come to conclusions when we have smaller sets of data and simpler models to describe that data. The larger the data sets, the more sophisticated the models, the more questions there are in understanding what the true distributions of those variables should be. And so we rely on other methods to help test the generalizability of those more complex models. For example, models with changing parameters based on sample size are also models that are known as nonparametric models that are not good candidates for this typical or at least more classical approach to inferential statistics and deriving p-values. So in these cases, we rely on other types of methods to be able to test the suitability of models and their application to making predictions in data that that the model has not actually been trained on. In other words, how well does it apply to a population? We use train, test, and validation splits as one way of confirming the suitability of models, or a more sophisticated approach is to use cross-validation techniques with k-folds. Each of these use different evaluation metrics that depend on what type of model you're using for determining the generalizability and performance of that model on data that it likely hasn't seen in the past and that you want to be able to apply it to in the future. One of those example statistics might be the performance of mean squared error. P-values in these contexts become less and less useful because we have to drop more and more assumptions about the underlying distributions that we're trying to relate those models to. So thanks very much for listening in today, and hopefully this was insightful in helping you to understand the relationship between descriptive statistics, inferential statistics, particularly kind of the classic approach to inferential statistics and the use of p-values, and how we leverage them in more modern machine learning contexts. If you want to run through an entire pipeline of data science as it applies to businesses today, feel free to check out my book, From Zero to Neural Nets in 60-ish pages. It's available for free from my website at fastdatascience.ai. Thanks again for listening. Please feel free to comment, ask questions, subscribe. I'm always looking for ideas on new content as well. Look forward to doing more of these with you in the future. Bye.